All right, so I'm going to show you guys a pretty cool proof. It just came out. Usually, like, I show old stuff that's been like around for hundreds of years. Today, I'm going to show you guys a Pythagorean Theorem proof, because you guys have all heard of the Pythagorean Theorem, a squared plus b squared equals c squared. We talk about it in this class all the time. Any right triangle, ABC, where the right angle is the angle opposite C, the hypotenuse, and for the purpose of this proof, we're going to make A the short side. Okay, we're going to have a short side and long side of this right triangle. The way they did this proof, and they just proved it, it was two high school students from New Orleans did this proof. I think they published it in March or something, and it's like there's all these different Pythagorean Theorem proofs out there, but this one is just like crazy cool. I've never seen it done like this before, and I wanted to show you guys in class. And the reason is it depends on the law of sines. It depends on two things. It depends on the law of sines, and it also depends on these two infinite series formulas. Now, depending on who you guys had college algebra from, you may or may not have seen these, but if you look in any college algebra textbook, they'll have one of these two fractions. And this fraction equals this series, this fraction equals this series, and it's easy to manipulate and go back and forth between those. Well, we're actually going to use both of those today, so I went ahead and listed those on the board for you guys. But here's how their proof goes. So they start by taking any right triangle, and then they build onto it. They take the same triangle, and they flip it over. Let me make sure everyone can see that. They flip it over on the other side, and they draw a reflection of the same size triangle. So now, this angle, oh, I forgot to say, this is angle beta, this is angle alpha in the original red triangle, and then they draw another triangle the same size on the other side of it, which means this angle up here is going to be 2 alpha. And what else do we know? We know that this is also C units, and this is another A over here, which means this length is now 2A. So that's the first part of their proof. Now the next part of their proof is you take this point right here, and we're going to draw a perpendicular line down in this direction. So let's make a perpendicular line here.
Professor Mickelson.
Yeah, can you hear me okay?
I can hear you, but I think you're out of frame for me. I can't see anything.
Let me zoom out. Thank you for asking. I'll zoom out so you guys can see it.
Thank you.
There we go. Is that better?
Yes.
There we go. Okay. And let me maximize this so I can see better too. All right. Okay. So again, to recap, the red triangle is the original right triangle, ABC. We take that triangle, we flip it over here, we draw the same size triangle here. So now, that's still angle beta. This angle up here is now 2 times alpha, and this side here is now 2 times A, which I'm going to rewrite because it's kind of messing up my little perpendicular line here. So this is 2A. And then I'm going to extend this perpendicular line that I had as far as I go until I have a point of intersection, because I'm also going to extend side C over here until the 2 lines cross, and they will always cross. Doesn't matter what your right triangle looks like, they will eventually intersect. So that's the next part of it. So we take the triangle, we flip it, and then we draw a perpendicular line, meaning this is a right angle right here. So that's the next part of their proof. Now, they call this side X, and this side Z. So they name those two sides. And then the next thing they do is crazy genius, but this is what they do. They take all of this empty space in here and they draw consecutive diminishing size right triangles that are all similar to the original right triangle. So they go right here to this point and they go straight down and they repeat that over and over again. So this is a right triangle, and then they go across. And they have this right triangle, and they keep going all the way down into infinity. They have an infinite set of right triangles that they pepper throughout this space. So let's take a look at the first right triangle, this first one that we made right here. We know that this side is 2a. We know that side is 2a. What else do we know? Well, we know that if this angle here is beta, this little angle has to be alpha, which means this little angle here is another beta. And that's a 90-degree angle, so that means this angle is alpha, and this angle is alpha all the way on down, which shows you that these are all similar triangles all the way down. On both sides, too, they're just different positions. So this is alpha up here, that's beta, that's alpha, that's beta, and so on until infinity. So what they did is because they're similar triangles to the original one, we're going to find the length of x1. x1 is the distance of the hypotenuse of the largest right triangle. That's x1. And let's see, because all of these triangles are similar, I know the hypotenuse over the long side, which is x1 divided by 2a, is supposed to be the hypotenuse over the long side of the original right triangle, which would be c over b. So you just take that and solve it for x1, and it turns out x1 is equal to 2ac divided by b. So that's x1, 2ac divided by b. Now, if we continue using the similar triangles formula, we're going to find out that x2 is 2a cubed c over b cubed. x3 is 2a to the 5th times c divided by b to the 5th, and so on. And what is x? X is the sum of all of those. X is x1 plus x2 plus x3 up to infinity. The sum of all of these little hypotenuses, or hypotenusi, or hypotenusan, or whatever it is. But the sum of all of those is equal to x. Now, I'm not going to show you the whole thing with z, but z is the similar idea, where we're going to call this z2, z3, and z4, and I don't really care. z1 is just c, so I'm just going to leave it at c. So that's z. z is c plus z2 plus z3 plus z4, and so on. So I've got all of my x's, x1, x2, x3, and so on, which is this infinite series. The same thing goes for z, and I've got z written down here. Let me copy down z. So z, if we write it as an infinite series, is c plus 2c, 2a squared c over b to the 4th, plus 2a to the 4th c over b to the 4th, plus 2a to the 6th c over b to the 6th, and so on. And you'll notice x1, x2, x3, z2, z3, z4, they're all changing by a smaller factor of this ratio, and we're going to call it p. A squared divided by b squared. That's the factor by which these triangle sides are shrinking as they get smaller and smaller and smaller. Remember, a was less than b. When we decided this triangle, we knew that was the short side, that was the long side. So a squared divided by b squared is that ratio that keeps making these sides get smaller. So what I'm going to do is a little substitution here. I'm going to make x equal to, and if it's a sum of all those, you'll see I can pull a 2ac out of x, 2ac divided by b, and that leaves me with 1 plus a squared over b squared plus a to the 4th over b to the 4th, and so on forever and ever and ever. That's another way of writing x. I'm just factoring this out. Z has a similar property where z looks like this, which is c plus 2c times a squared over b squared plus a to the 4th over b to the 4th, and so on. So we've got x and z defined as these infinite sequences. Now I'm going to do something that's going to make it look a little prettier. Remember, p is equal to a squared over b squared? So this is ac over b times 1 plus p squared plus p cubed, and so on. And down here it's c plus 2c times p plus p squared plus p cubed, and so on. All right, so there's my two infinite series, and this is the first part of the proof that these ladies from New Orleans did. That, again, you may not have seen this class, but you might have seen it in the previous class, where we do this little substitution. We have these two formulas for an infinite series, and we're going to sub those in. So this is 2ac divided by b times 1 plus p plus all these higher powers is 1 over 1 minus, and p, which again is a squared over b squared. Same thing goes for down here. We're going to sub that in. That's c plus 2c times this formula, p over 1 minus p, which is going to be a squared over b squared divided by 1 minus a squared over b squared. So we're subbing that back in. So now I've got expressions for x and z, and they're not very pretty expressions. So we're going to take a look at how to manipulate those. I'm going to have to erase a little bit, sadly. So let's do that. We're about halfway done with the proof, in case you guys are wondering like what kind of time frame we got here, if you're trying to hold it or whatnot. So there's x, and again, x equals 2ac divided by b times 1 over 1 minus a squared over b squared. And that's not a very nice expression. Looks like you guys still can't see that very well, so I'll move that over there. Okay. I'm going to clean up this fraction by multiplying top and bottom by b squared. That's going to clean this fraction up. So I get 2ac over b times b squared over b squared minus a squared. And I can do a little bit of cancellation. That b cancels with one of those b's on top. And there's x. 2abc divided by b squared minus a squared. So that's x. And I can do the same kind of thing to z. I can do these same kind of steps to z over here. And I'll just show you a simplified version of z. If you simplify z all the way down, you get c divided by b squared plus a squared divided by b squared minus a squared. So if you simplify x all the way down, you get this. If you simplify z all the way down, you get this. Now, why are x and z important? Should be your next question. I missed my old classroom where I had whiteboards on 3 sides of the room. And I'm slumming it with this lonely whiteboard. All right. So here's why x and z are important. Remember that triangle we built? Where that's the right angle? This is x, and this is z. This angle up here was 2 alpha. So I know the sine of 2 alpha is equal to opposite over hypotenuse, x over z. And here's my two expressions for x and z. And if I'm going to divide those, I'm going to have to invert and multiply z. So this is 2abc divided by b squared minus a squared times the inverse of z, which is b squared minus a squared, over c times b squared plus a squared. And that's pretty sweet because cancel, cancel. So the sine of 2 alpha is equal to, oh, one more thing cancels, the c's cancel, equals 2ab divided by b squared plus a squared. Okay, so now we're on the home stretch. All we have to do is apply the law of sines, because we haven't really talked about the law of sines yet. So let me make some space for that to happen. So let's go back to the top part of this triangle. And I'm going to redraw it over here where it looks like this. Where this triangle was 2a, this was c, this was c, this was beta, and this was 2 alpha. So let's recall this triangle. Where again, this is the first triangle we made when we reflected the red right triangle around. We made this triangle that had a double angle on top and 2 times a on the bottom. If we look at this triangle, if we apply the law of sines, we also know that the sine of 2 alpha divided by 2a is equal to the sine of beta divided by c. So if I take this same expression, I take this proportion equation, this law of sines equation, and multiply both sides by 2a, I get sine of 2 alpha is also equal to 2a sine of beta divided by c. And the only thing I don't like about this is there's a sine of beta in here. Oh, wait a second. Let's look at that original right triangle where that was beta, and this was b, and this was c. I know the sine of beta is b over c. So I can rewrite this as 2 times ab divided by c, so it's divided by c squared. So the sine of 2 alpha is equal to 2a over c squared, 2ab over c squared. It's also equal to 2ab over b squared plus a squared, which means 2ab over b squared plus a squared is equal to 2ab over c squared, because they're both equal to the sine of 2 alpha. Well, guess what? If you have equivalent fractions and the numerators are equivalent, the denominators must be equivalent. There it is. There's the Pythagorean theorem, and that's how they proved it. These two girls from high school in New Orleans were able to figure this out with a couple substitutions of infinite series and the law of sines. It was all about the creativity of drawing that triangle and peppering in all those triangles inside and adding all those hypotenuses together, hypotenuse in, whatever, and coming up with that. Super cool idea. I was like super thrilled about it. But anyway, because we just learned the law of sines, I wanted you guys to see that proof, because I almost guarantee you guys have never seen